Hello, this is problem set number 2, problem 5. A cylinder 1 meter tall with inside diameter 0.12 meters is used to hold propane gas for use in a barbecue. Propane gas has a molar mass of 44.1 grams per mole. It is initially filled with gas until the gauge pressure is 1.3 times 10 to the 6 pascals at 22 degrees Celsius. The temperature of the gas remains constant as it is partially emptied out of the tank, until the gauge pressure is 3.4 times 10 to the 5 pascals. Calculate the mass of propane that has been used. Okay. And over here to the left, I have a picture of what the cylindrical tank would look like with the inside diameter of 0.12 meters and a height of 1 meter. Okay. And very quickly, I just want to point out some things that we're going to be using in this problem, and I'm pointing it out because I also hope you know this, or you have this in your formula sheet or cheat sheet so that you could use it on a test or even for homeworks. So the first one is molar mass. Molar mass is equal to the total mass, little m, over moles, little n, or the amount of gas in moles. Okay? That's important to know. The other thing is whenever you have the unit pascals, that is equivalent to the unit kilogram over second squared times meter. Okay, so these units are interchangeable, which we will do that in this problem. The other unit that is also interchangeable is joules and kilogram times meter squared over second squared. Okay. And lastly, the two values of R, which are equivalent, right? These two values are the same. They're both R. The only thing is one value has a unit of joules per mole over Kelvin, and the other value has a unit of liters times ATM over mole times Kelvin. So it's just up to you which one to use for a problem. And usually that depends on the units that you want to cancel out. Okay. All right, so back to the problem. Some of the givens that we have is molar mass, and that is 44.1 grams per mole. Okay. Other given that we have is the initial pressure gauge with a value of, so initial gauge pressure and that value is equal to 1.30 times 10 to the 6 pascals. The other thing that was given was the temperature, which according to the problem, the temperature remains constant. So the initial temperature is the same as the final temperature, which is equal to, so let's just call that T, and that is equal to 22 degrees Celsius. Okay. The other thing is we're also given the final gauge pressure right here. And that is, so final gauge pressure has a value of 3.40 times 10 to the 5th pascals. Okay. And we want to know the mass of propane used, right? So that's this guy. That would be the mass of propane used would be our initial mass, M1, subtracted by the final mass, M2. And that would be the mass of propane used, okay? All right, so in order to solve this problem, I'm going to use the equation from chapter 18, section 1, which is ideal gas law equation. right? And that is PV equals nRT, right? And just so you guys are aware, in case you're not, this pressure in the ideal gas law equation is atmospheric pressure, or sorry, absolute pressure, okay? And the temperature is temperature in Kelvin. All right. So in order to get the absolute pressure from the gauge pressure, right, of the tank, we have to also add atmospheric pressure to the gauge pressure, and that would give us the absolute pressure, okay? So I'll write that down. I'll write it down in red, just so it's clear. So absolute pressure is equal to gauge pressure, which we were given right here and right here, plus atmospheric pressure. Okay. So let's do that. Let's convert our initial gauge pressure and final gauge pressure to the initial absolute pressure and final absolute pressure. So P1, we'll call that the absolute initial pressure, is equal to the gauge pressure, right, which is 1.30 times 10 to the 6 pascals, plus atmospheric pressure, which is 1.01 times 10 to the 5 pascals, okay? And that is the value for atmospheric pressure. So maybe you should also have this in your formula sheet, but that is the value for atmospheric pressure, unless stated otherwise. Okay, and so the absolute initial pressure would be equal to 1.40 times 10 to the 6 pascals. Okay. And for the final absolute final pressure, it would be P2 is equal to 3.40 times 10 to the 5 pascals. That's just this guy. That was the gauge pressure that was read, plus atmospheric pressure, which is 1.01 times 10 to the 5 pascals. Okay? So the absolute final pressure would be equal to 4.41 times 10 to the 5 pascals. Okay? And the reason why I converted the gauge pressure to absolute pressure right here is because I need the absolute pressure to use the ideal gas law, right? And to do that, you would just add atmospheric pressure to the gauge pressure, and that would equal absolute pressure. Okay. And then obviously temperature in Kelvin, that's pretty easy, right? I would just add 273 to the given 22 degrees Celsius right here. And I could do that on my calculator, and that would equal 295 Kelvin. Okay? So temperature, which according to the problem remains constant, is 295 Kelvin. Okay? So now let's try to use PV equals nRT. Oops. So ideal gas law, PV equals nRT. There's actually two ways to solve this problem. First, we would convert this N, the amount of gas in the ideal gas law, with what's given to us, which is molar mass, and we're also looking for total mass, right? So the first way to solve this is if PV equals nRT could be converted, right? This could be converted to using this formula, this equation. This would become PV equals total mass divided by molar mass, which is the equivalent to N, times RT, right? And this is given, right? That's constant. This is also a constant, R. M was given, that's right here. And the volume doesn't change. That's this guy right here, right? The cylindrical tank. So I could rewrite this equation with the constants on the right side and the things that change on the left side, right, from initial to final. So I know my pressure changes because I have an initial and final pressure. I know my volume doesn't change because the cylindrical tank doesn't change shape or anything like that. My mass right here, that will change, right? Because that's what we're looking for, the mass of propane that was used. So the initial mass will be different than the final mass. Molar mass doesn't change. And like I said, R doesn't change and temperature doesn't change in this problem. So let's do pressure over mass is equal to RT over volume times molar mass. Right, that's another way I could write this down. Okay, and like I said, everything here on the right side of the equation, that's a constant, right? And because that's a constant, I could say, okay, so my initial values would be the initial absolute pressure divided by initial mass is equal to RT over Vm, right? The constant R times temperature divided by the volume and the molar mass. And final values, okay, that would be my final pressure divided by my final mass, and that would still equal the same thing. The constant R, the temperature that doesn't change, the volume of the cylindrical tank that doesn't change, as well as the molar mass for propane that doesn't change, right? So because that doesn't change, again, everything here, this guy right here and this guy are equal, right? And as a result, therefore P1 over M1 is also equal to the final absolute pressure over the final mass. mass of gas, right? Okay. And we have the initial pressure and we have the final pressure, right? That's what we solved here. Absolute pressures, the initial absolute and the final absolute pressure. Okay, but we don't know these guys, the initial mass or the final mass. So we will use, again, the ideal gas law equation to solve for the initial mass, or you could also use the ideal gas law equation and solve for the final mass. It's up to you. I'm going to go with the final mass. So ideal gas law equation, PV equals nRT. And I'll use initial, right? This is for initial, so I could get my initial mass. Again, I'll rewrite this, like I said, as PV equals, right here, N can be substituted as initial mass. That's my initial pressure times the volume of the cylindrical tank is equal to the initial mass divided by the molar mass, which is a constant, times R, the constant R, which is constant, and the temperature, which doesn't change in this problem, right? And so I'll just rewrite this equation to find M1. So my initial mass is equal to initial absolute pressure times the volume of the cylindrical tank where the propane lies, right? And that is multiplied by the molar mass and divided by the constant R and the temperature in Kelvin, okay? All right, so let's just plug that in from what we have. So that is equal to, right here, P1, absolute pressure for P1 is 1.40 times 10 to the 6 pascals times the volume, which is the volume for a cylinder is area of this guy right here. Oops. The area of this inside diameter, right? Which is going to be, area is pi r squared, right? Pi r squared. And that's the radius of the inside diameter of the cylinder right here, circled in right here, okay? Times height, which is 1 meter, right? And then multiplied by the molar mass, which is given right here. So times molar mass divided by R T, okay? I'm going to plug my values in right now. So pi r is 0.12 divided by 2. Right, that's this guy, divided by 2 because that's the diameter. So r would be 0.06 meters. So 0.06 meters squared times the height. And the height is, let me clear this up real quick. So that's 0.06 meters squared. Squared. And the height is 1 meter. So 1 meter times 1 meter times 1 meter. So that's pi r squared h. And the molar mass is given to us here in grams per mole. I'm going to change that to kilograms per mole. And that's 0.044 kilograms per mole, right? I just changed grams to kilograms. So times 0.044 kilograms per mole. Okay. And for R, I will use joules because I know that joules, I'm going to use this value of R with joules per mole times Kelvin because I know joules has kilograms, meters squared, and seconds squared that I could use. And that's eventually what I want to convert to. So R is times 8.31 joules per mole Kelvin. Okay, and temperature is 295 Kelvin, right there. So times 295 Kelvin, okay? So I could now solve for my initial mass in the tank. But I want to get kilograms as a final unit, and I see that for some reason I have pascals and I have joules, right? And I just want to get rid of that. So I'm going to convert pascals to kilograms per second squared times meter, and I'm going to convert joules to kilograms times meter squared over second squared, okay? All right, so I'm going to do that. So now that is equal to 1.40 times 10 to the 6th. And pascals is the same as kilograms per second squared times meter, right? And times pi times 0.06 meters squared times 1 meter. Okay, I'll change the color of this guy so that's that outer parentheses. Okay, and times 0.044 kilograms per mole. Okay, I'm going to divide that by 8.31, and instead of joules, I'm going to convert it to kilograms times meter squared over second squared. So, like I said, kilograms times meter squared over second squared, and that's only the joules part. I still have to add the mole over Kelvin part, right? So times mole times Kelvin, right there. Okay, and the 2 times 295 Kelvin. Okay, and that is my M1, my initial mass. So now I could plug that in my calculator, right, and cancel out all the units. I would end up with M1 is equal to 0.285 kilograms. Okay. And now I can plug that back into this equation because I have P1 right here, I have P2 right here, and I have M1 right here. So I could solve for M2. Okay. So if P1, I'm just going to bring this equation down. So if P1 over M1 equals P2 over M2, so I could solve for M2 because that is just going to be equal to P2 times M1 divided by P1, right? Okay, and I have all those values, right? So P2 is equal to 4.41 times 10 to the 5 pascals right here. So P2 is equal to 4.41 times 10 to the 5 pascals. M1 is equal to 0.285 kilograms. And divide all that by P1, which we said was 1.4 times 10 to the 6. Okay. 1.40 times 10 to the 6 pascals. Okay. So my pascals cancel out and I'm left with kilograms as the unit. And if I plug all that in the calculator, I would get my my final mass is 0.0897 kilograms of propane, right? Okay. So again, what were we looking for? We were looking to calculate the mass of propane that was used, right? And that's basically M1 minus M2. Initial mass minus final mass equals mass of propane used. So we could do that now because we have the initial mass. So M1 minus M2 is equal to 0.285 kilograms minus 0.0897 kilograms. And if you subtract that, then you would get the mass of propane used is equal to 0.195 kilograms. And that is your final answer.